Hi all, today we discuss section 22.16g gGraeffes root square method. This method has a great advantage over the other methods that it does not require the prior information about the approximate values. That means all other methods we have started with an initial approximation obtained using the fact that f of a less than 0, f of b greater than 0 and all. But this method is applicable to only to polynomial equations. Okay, we cannot apply this method to an arbitrary algebraic equation. So this is applicable to only for polynomial equations. Nevertheless, it is capable of giving all the roots of that equation. Okay. And the other methods we have seen that the other methods will give on only one root of that equation. Okay, but this is capable of giving giving the information about or approximate value about all the roots of this of the polynomial equation. Okay, so I'll explain this with an example. We start with a polynomial equation. Say x cube minus 2x square minus x plus 2 equal to 0. Okay, so we call this as f of x. So we have the equation f of x equal to 0. So we start with this equation and we collect the odd powers in the left side and transpose all the even powers to the right hand side. So you can get x cube minus x in the left hand side, and we have 2x square minus 2 in the right hand side. Now we square this equation. Okay, squaring, we can get x cube minus x whole square equal to 2x square minus 2 whole square. Okay, we are squaring both sides. Then we can get the equation x raised to 6 minus 2x raised to 4 plus x square. So this is the left hand side. Then right hand side will be 4x raised to 4 minus 8x square plus 4. Okay, now this equation is of degree 6. Okay, so we reduce this equation to the degree 4 by putting u is equal to x square. Okay, by putting u equal to x square, we can get the above equation will be, in terms of u, we have u cube minus this 2 times u square plus u, that is equal to 4 u square minus 8u plus 4. Okay, so this is the equation. Now we again collect the odd degree terms in the left hand side and transpose all the even degree terms to the right. Now you can get this becomes u cube plus 9u. This is because of transposing this minus 8u to the left side. That will be equal to 6u square plus 4. Okay, so this is the new equation. Now again we squaring, we can get u cube plus 9u whole square equal to 6u square 6 equal to 6u square plus 4 whole square. Okay, then squaring this, we can get this equation as u raised to 6 plus 18u raised to 4 plus 81u square equal to 36u raised to 4 plus 48u square plus 16. Okay, now we can substitute to reduce the degree of this equation. Substitute z equal to u square. Okay, so z equal to u square, by putting this we can get u raised to z, in terms of z we can write z cube plus 18z square plus 81z equal to 36z square plus 48z plus 16. Okay, now you transpose the odd degree terms to the left and even degree terms to the right, then this becomes z cube plus 33z. So this is because of this 81z and 48z. Now that is equal to 18z square plus 16. Okay. Again, squaring we get, squaring both sides we can get z raised to 6 plus 66 z raised to 4 plus 1089, that is the square of 33 z square equal to 324 z raised to 4, that is 18 square, plus 576 z square, that is 2 times 18 times 16. Now we have z square, then we have 256, that is the square of 16. Okay, so this becomes the equation z raised to 6 minus, you can repeat this process as many times you want, but I stop squaring. I have squared the equations 3 times. First time is here, and second time is here, and third squaring is here. So we have the equation z raised to 6 minus 258 z raised to 4 plus 513 z square minus 256 equal to 0. Now you reduce the degree of this equation by putting y is equal to z square. Then we can get, in terms of y, we have y cubed minus 258 y square plus 513 y minus 256 equal to 0. So in terms of this y, we can get a new equation. So this is obtained by squaring our original equation 3 times. Okay, so this is the new equation. Now we have how to find the solutions of, how to find out the roots of this equation. So this is obtained if you put this is equal to the coefficient of this equation as by comparing this as lambda naught y cube plus lambda 1 y square plus lambda 2 y plus lambda 3 equal to 0. Comparing this equation to this, you can get the coefficients as lambda naught is equal to 1, lambda 1 is equal to minus 258, lambda 2 is equal to 513, lambda 3 is equal to minus 256. So using these coefficients, you can write the roots of this equation. If this y1, y2, y3 are roots of, we know that this equation has only 3 roots, so roots, then we can write y1 is equal to minus minus lambda 1 by lambda naught. So that is I'll write the minus of minus 258 by 1, and y2 will be that the second one, that is y, that is 513 minus of 513 divided by this minus 513 by minus 258, and y3 will be minus 256 by 513. So that is that means using the coefficient of this, you can write the y1 as minus lambda 1 by lambda naught, and y2 as minus lambda 2 by lambda 1. Y3 has value minus lambda 3 by lambda 2. Okay, so this is the way we obtain the solution of this equation. So there is a derivation in the textbook that how to get these solution. These are the approximate solutions. So there is a derivation given in your textbook how to derive this roots. So I am going to use this one. We are not going to derive this formula. So using the coefficients of this, by squaring 3 times the original equation, we can get a new equation. Using the coefficients of these equations, we can get the solutions, the roots of this equation itself. Okay, so this is the solution of this equation. But our original equation is this one: x cube minus 2x square minus x plus 2 equal to 0. Okay, so if these are the approximate values of this solution is y1 is equal to 258, y2 is equal to the original value is 1.988372, and y3 is equal to 0.49902. so these are the values, but we know that we have substituted y as our z square, and z is nothing but u square, then and u is nothing but x square. Okay, so we have x square whole square we have, this is x raised to 8. So this is the relation between x and y. Okay, so y is equal to x raised to 8, then y1 can be written as x1 raised to 8. So the roots of the original equation x1 is obtained by taking the 8th root of this y. So that is y1, x1 is written as y1 raised to 1 by 8. So that is equal to 258 raised to 1 by 8. So that is nothing but 2.00194. And the x2 is obtained by y2 to the power 1 by 8. What is y2? y2 is 1.988372 raised to 1 by 8. So that is equal to x2 is 1.089713. And finally we have x3. The approximate value of x3 is 0. This is obtained by taking the taking y3 is our y3 raised to 1 by 8, that is equal to 0.49902 raised to 1 by 8, that is equal to 0.916771. So these are the values of x. But we know that we already mentioned that these formulae are obtained by some kind of derivation. So in that derivation we have used some or we have restricted our discussion to the modulus of those coefficients of the final equation, that is mod lambda 1 by mod minus lambda by lambda naught, and etc. So whenever we obtain these equations, x1 is equal to this is approximately 2, and x2 is equal to approximately 1, and x3 is approximately 1. So these are three approximate values of our original equation. So we need to we need to verify the signature of the sign of this roots. That means we can expect only the possibilities x1 as plus or minus 2 and plus or minus 1 and plus or minus 1 here, because we have used some kind of restrictions in the derivation of this formula. So please verify that the next step is to verify the sign of these values. x1 is equal to plus or minus 2, x2 is equal to plus or minus 1, x3 is equal to plus or minus 1. So how will you find out the sign? So first you consider that equation f of x equal to, this is the original equation, x cube minus 2x square minus x plus 2, and substitute for minus 2 first. Okay, what is f of minus 2? F of minus 2 is minus 8 and minus 8 again, 2 into 4, that is plus minus of minus 2 plus 2. So this will give minus 16 plus 4, that is not equal to 0. So from this you can say that this f of minus 2 is not equal to 0, so minus 2 is not a solution, and you evaluate f of 2. What is f of 2? 8 minus 2 into 4, that is 8, and minus 2 plus 2, that is equal to 0. Then you can get the sign of this 2. So explicitly you can write x1 is equal to 2 here, and similarly you can show that x2 is equal to 1 and x3 is equal to minus 1. That means 1 and minus 1 are the solutions of this equation. So this is the way we solve the or find the roots of the equations of the original equation using Greiffes method. So once you got these values, x1 is this and x2 and x3, then you can stop the procedure up to this point. You can say that these are the approximate values of the original equation. So you need not worry about all the further procedure of this method. So this gives all the roots of this equation. That is the advantage of this gGraeffes method. Okay, next we can see some problems in the textbook. There are some equations whose roots will be complex numbers and the other repeated roots, etc. So we can see how will you solve those problems using gGraeffes method. This is the first example in the textbook. Apply gGraeffes root square method to solve the equation x cube minus 8x square plus 17x minus 10 equal to 0. So first of all, you need to use some idea of Descartes' rule of signs. So that gives the idea of the roots, how many of roots are real and how many of roots are positive and negative and complex, etc. So that is that can be checked using the sign of change. That means the sign, the changes of the sign in the equation. So if you consider this f of x equal to this x cube minus 8x square plus 17x minus 10 equal to 0, you need not worry about this the observation of getting the number of real roots. So you need not worry about this. You can leave this one and you can start with this step. First, since this is included in the textbook, I will explain this again. This x cube, when you consider the signs of these terms, the first term is positive, that is the coefficient of x cube is positive, and when you consider the second term, the coefficient is negative, and third is again positive, and finally the coefficient is negative. So from this you can say that the change of signs as we go through these terms, you can say that here we have first change, this plus is changed to negative, then there is one change here, and here again we have one change, and here again one change. So totally we have three positive real roots. Okay, so this indicates that there are three positive real roots. Okay, so that is the observation from the this inference. So we can this equation f of x is a third degree polynomial. So we know that it has at most three real roots, at most three roots, but we know that there are three positive real roots. So all the roots of this equation are real and positive. So we can find out all those roots. So first we collect all the order terms in the left hand side. So that is x cube, that is in fact that is x cube minus x cube plus 17x equal to 8x square plus 10. So this is the first way of writing or collecting the odd degree terms in the left and even degree terms in the right. And for the convenience, we take x outside from these equations. Then by putting in this textbook, they are putting the value of this x square as y before squaring this, or you can square this equation and then substitute this x square is equal to y. So first of all we substitute this, then you can get x square is equal to y here. Then we can write this y plus 17 whole square 8y plus this 10y square. So we can write on the other way, you can write this x cube plus 17x square equal to 8x square plus 10 whole square. So first of all you square this one and then substitute. Okay, squaring both sides and substitute, then you will get this one. Okay, by squaring this, you can, from this equation you can write x square plus 17 whole square plus 8x square plus 10 whole square. Now putting before expanding this, before squaring this, you can substitute for this x square, that is equal to y, and x square is equal to y plus 17 whole square, and you can square this. When you square this, you can get this one. Okay, again you collect all the order term in the first left hand side, then you can arrange the equation in this manner, and squaring again by substituting squaring and substituting y square is equal to z, you can get this equation. Okay, so rearranging this, you put z square equal to u, that means this the squaring of third time, you will get this equation. Okay, so finally you write after squaring 3 times, you can get a equation like this. Okay, then we know that how will you find out the roots of this equation, that is using the fact that minus lambda 1 by lambda naught, that lambda naught is 1 here, so O raised to minus 1 by 8, so that is equal to 39088 O raised to 1 by 8, so that is this one, approximately this is 5. Okay, now I will get P2, that is obtained by minus of this divided by this. Okay, that will be minus lambda 2 divided by lambda 1. This is in fact lambda, this is 1, then that is lambda naught, and this is lambda 1, this is lambda 2, and this is lambda 3. So using this minus lambda 2 by lambda 1 whole raised to 1 by 8, that will be this one, then that is approximately 2. And P3, we have Q3 raised to, Q3 is the 0 of this one, Q3 is the root of this equation, so that is obtained by minus lambda 3 by lambda 2, so that is this one, so that is equal to 1. So from this you can say that these are the solutions of the roots of 3 roots of the original equation. Okay, so this is the one way of getting roots of the polynomial equation. Okay, so this gGraeffes method is effective only when these the magnitude of these roots are different. Okay, so if this will give, this method will work more effectively if the original roots x1, x2, x3 satisfies the fact that mod x1 is much greater than this, mod x2 is much greater than mod x3. In this case we have more accuracy while we using this gGraeffes method. After getting these values, you need to verify that we will assume this plus or minus 5, plus or minus 2, plus or minus 1 are the possible roots of this equation. Then by substituting these values to the original equation, you can get the sign. Then by substituting, and you can see that f of 5, f of 1, f of 2 are 0, so we have 5, 2, 1 are the solution roots of the equation. Okay, now we have another example. This is second example in the textbook. Find all roots of equation x raised to 4 minus 3x plus 1 equal to 0. So using gGraeffes method, we will find the solution of this. Here we can check the solution of we can check the number of real roots and positive real roots and negative real roots. So this, when you consider this one, we have the first term is positive, the second term is negative. We can neglect the term containing x cube because the coefficient is 0, so we don't worry about that. We can neglect that term, and the other term will be negative 3, that is negative sign, then we have plus. Then from this you can say that there is one change in this and one change is nil, then totally we have 2 positive real roots. Okay, now if you consider f of minus x, by putting x equal to minus x in this equation, we can get this equation x raised to 4, x raised to 3x plus 1. Then from this you can get the change of sign as plus, first term is plus, second term is plus, third term is plus. There is no change here, there is no change here, so we can say that when you consider f of minus x, there is no, this number indicates the number of negative real roots. Okay, so we know that 0 negative real roots. Okay, so it has only 2 real roots. Both real roots are positive, and we have the other roots are complex. Okay, these are the only possible real roots, so that means this is an equation of degree 4. Therefore 2 of them are real roots, and in fact this positive roots, and other two will be the complex roots. Okay, so when you apply the gGraeffes method to this equation, all the roots can be identified. Okay, so first of all we write this x raised to 4 minus 3x plus 1 equal to 0 as x raised to 4 plus 1 equal to 3x. Okay, and squaring and putting x square equal to y, you can get this one. I'm not going to elaborate this again. And substitute y square is equal to z, then you can get this one. And expanding this, you will get this equation. Now again put z square equal to u in this equation, then you will get this equation, and expand using the binomial expansion. This is a plus b plus c whole square. We know that a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ac. Using this formula, you can expand the left hand side, then you will get this. Okay, now we have squared 3 times. Then we can list the solution of roots of this equation, the final equation p1, p2, p3, p4. If these are the roots of the this p1, p2, p3, p4 are the roots of the original equation, and q1, q2, q3, q4 are the roots of this equation. This is equation number 3. Now we can obtain p1 as q1 raised to 1 by 8. This is because the connection between this u and x. Okay, this u is nothing but z square, and z is our y square. So this is y raised to 4, and we know that y is equal to x square, so this is x raised to 8. So we can connect this x and u in terms of 8th root, that is x equal to u raised to 1 by 8, and q1 is the root of this equation, then q1 raised to 1 by 8 will give the root of the original equation p. So that is obtained here. Then we have 4 values p1, p2, p3, p4. Okay, so now our idea is to track the real roots and complex roots. Okay, so all these values are real. Okay, so first of all we observe that these equations. So observe these equations. After substituting, we have expanded this and this equation and the original equation. Okay, so we have 3 such equations. All these equations, we can observing this equation, we can say that these are unchanged. Okay, that is the last term. The last term is unchanged throughout this squaring. Okay, that means this is 1 and this is 1, and similarly when you observe these two equations, we can say that these coefficients are the magnitude of these coefficients. Okay, the coefficient of z cube or coefficient of u cube are unchanged. Okay, the magnitude is are unchanged. So if we write these values, as the coefficient as this is lambda naught, this is lambda 1, lambda 2, lambda 3, lambda 4, then we can say that lambda 4 and lambda 1 are unchanged using the in the equations 2 and 3. Okay, so using that fact, we can say that from 2 and 3 we observe that magnitudes of coefficients lambda 1 and lambda 4 have become constant. Okay, only the magnitude. While you considering the second equation, lambda 1 will be 4. Okay, this is 4, and in the other equation lambda 1 will be minus 4. Similarly, lambda 4 is 1 and lambda 4 in the last equation is again 1, so this remains constant. So then we can observe that p1, p4 are real and real roots. Okay, that means when you consider the other lambdas, lambda 2 and lambda 3, all these equations, this lambda 2, lambda 3 are changing in magnitude, and both magnitude and sign, so we can expect those P2, P3 will give or this corresponds to the complex number. That means using this P2 and P3 we will find out the complex roots. Using P1 and P2, P1 and P4 we can get the real roots. So we set P1 and P4 are real roots. Then using this P2 and P3 we will find out the complex root. Now we can see how to find the complex roots. So since this P2 is P2, P3 is real and complex, we call this as some PR and PR plus 1. So these are the complex roots. Then we will here this R is equal to 2. Then we can set this is the complex roots. Okay, suppose this is the complex root, then we have to evaluate row 2, this zeta 2 and eta 2. Okay, so from this you can say that this row 2 raised to 2 into 2 to the power 3 will give approximately, the thing is approximate, lambda 3 by lambda 1. Okay, from the final equation we can get this lambda 1, lambda 2, lambda 3, lambda 4, etc. So using this, since this PR is P2, then row 2 can be obtained by, that is the magnitude of the complex roots, so that can be obtained by this formula. That means row 2 raised to 2 into 2 raised to 3. So this is in general we can write that is row R raised to 2 into 2 raised to m. So this m is the number of times we have squared the equation. So here we have we have squared the equation 3 times. So we can replace this m by 3. So this will be obtained by writing lambda 3 by lambda 1. Okay, so this is also given in the derivation of the formula. So we just remember this one. If you are considering row 2, then we need to write this lambda 3 by lambda 1. In general, row R 2 to the power 2 times 2 to the power n will be obtained by using the fact that R plus lambda R plus 1 divided by lambda R minus 1. Okay, so this is the general formula. If you square the equation 8 times, then you can replace this n by 8 and the corresponding R, using R you can write this one. Okay, so that then from this equation you can get row 2 raised to 2 times 2 raised to 3 will be this one. Then obviously this lambda 3 is this one. This is our lambda 3 and this is our lambda 1. Lambda 1 is minus 4, lambda 3 is minus 5917. So by dividing this you can get this value. So this is the magnitude of the original equation, magnitude of the complex roots of the original equation. Okay, now we have to evaluate this zeta 2 and eta 2. So zeta 2 is obtained by this formula. So this is because if you have 4 roots, we know that if P1, P2, P3, P4 are 4 roots, then this will give the sum of roots. Okay, sum of roots is nothing but minus lambda by lambda 1 by lambda naught. So this is nothing but this P2 plus P3 will give the since these two are complex roots, then they occur in pairs. Then when you add these two complex numbers, then the imaginary part gets cancelled. So you can get 2 times the real part of this equation, this complex roots. Then we have P1 and P4 are there. Then this will give the sum of the roots. So from this you can get epsilon 2. How will you get epsilon 2? That will be minus a half times P1 plus P4. So this will give epsilon 2. We already know that what is P1 and P4 here. So using that P1 and P4 you can get epsilon 2. Okay. Similarly, using this epsilon 2 you need to remember this formula. This is the imaginary part of the equation. So that imaginary part of the complex roots. So that is eta 2 is equal to root of row 2 square. This is our row 2, that square minus epsilon 2 that is obtained from this equation square. So that will give 1.38111, etc. Okay, now we have obtained zeta 2 and eta 2. So using those two values we can get the complex roots. Okay, so using those two values we can write these are the complex roots, and P1, P4 will give the real roots. Okay, we know that these two are the real roots and these two are the complex roots. So this is the way we obtain the roots of that original equation. Okay, so if the roots are complex, you need to remember that these two formulas, that is the formula, this is the formula for getting the modulus of that complex roots, that is rho r, and using that rho r or rho 2 we can get the epsilon 2 and this eta 2. Okay, epsilon 2 can be obtained from the usual fact that the sum of roots will be minus b by a, that is minus lambda 1 by lambda naught, and using that lambda 2 and rho 2 you can get the value of this eta 2, which is the imaginary part of the complex root of the original equation. Okay, so this explains the last method, gGraeffes method. So please try to do the problems in the exercise, and we will schedule a Google Meet for all these topics, so we can conclude with this video. We can conclude the syllabus. Now the other classes onwards we will discuss the revision things, so you can come up with your doubts and we will interact in Google Meet. Okay, you can decide the time and date of the Google Meets in the further classes. Okay, thank you. So all the best for your examinations. Thank you.